So we are looking at splay trees, and it's why is the volume echoing? Yeah. Okay, we are looking at splay trees, and it's a kind of binary search tree. It's still echoing. How do I check? Yeah, it's okay. Okay, so we know that in a balanced binary search tree, when we are searching for a sequence, the best thing we can achieve is the order of log n time complexity. Now we are looking at, is this the best? We know that this is best in the worst case, but we want to know, is this best in the average case? So when I am given a sequence of access sequence, and then what is the best I can hope for the access sequence in any binary search tree? So that is the theme of the amortized cost analysis. So this is the amortized cost analysis, amortized cost for any data structure, right? If I am searching for a sequence, then the cost of the sequence by the size of the sequence, maximum of that. So now can you think of a sequence, say, which I will call the easy sequence, such that you get, say, order of 1.
Somehow know the root, you ask for the root, whatever you permute the sequence, you will always get the same cost then.
Yeah, say I
finding the root, searching for the root cost is O1.
Yeah, so you were saying that the sequence looks like, so if the root element is x1, say, the sequence looks like x1, x1, x1 like this. So this is a trivial. Can you give me a non-trivial example where this will be, say, order of 1? Okay, so if I say that I am allowed to search from the point I left in the previous search. So I am having an extra pointer, and I put that point, I don't search, start every search from the root, but I start every search from where I left. I have an extra pointer there. Then can you say of some easy sequence? The in order traversal basically, right? Yeah, so if I have a sequence like, so before I talk about the sequences, here today we will assume that our universe is totally ordered, since we are talking about binary search tree, that is essential. And it may be the case that there are information associated with the keys, but we are always looking for the key values, so we will assume that the key values are, so we will assume that the key is the set 1 to n, and we will be looking for a access sequence or the search sequence of length m, where m is generally larger than n. So, yeah, what was I saying? Yeah, so if I am looking at the like the sequence to be 1 to dot n, then if I do a in order traversal, I can, with order of 1 cost, I can access each element, right? So this is something which is called the sequential access. And we know of data structure which takes order of 1 time or order of m time for m length sequence, that is order of 1 time per search. So the amortized cost will be order of 1. So so I will come back to this about the easy sequence and hard sequences. So what we are trying to do is that we are trying to see if this is the best, and we are trying to come up with a heuristic such that I can do something better than. So if I am doing a search of m elements, this tell me it should be m into log n, but I am saying that is not the case. That is a very gross overestimate. I want to get a better upper bound for the search time. So for that we will be looking at this splay tree. So there have been many some other heuristics before splay tree came in. So this is I am doing from a paper of Tarjan of 1986, I think. Hmm, 85, Slater and Tarzan. Yeah. So okay, so the paper title is self-adjusting. Write it here. So as you can see, this is a very old paper, and still we'll end with an open question from this paper, which is still not resolved. So yeah, so there had been some other heuristics, and which has been successful, or rather proved to be good in list instead of trees. Yeah, so there is a heuristic called move to front, which means one second. Yeah, so now as you see, this is the binary search tree that we were talking about here, the balanced binary search tree or any binary search tree. Those are called static binary search tree, because when you were searching or inserting or when you were searching, you don't move around the keys. You just look for the key, you follow some path, and you say yes or no, but you don't do anything to the structure of the binary search tree. Now, as this title suggests, this is a self-adjusting binary search tree. What they do mean by the self-adjusting thing is that when you are searching for an element, when you are searching for a key, you are traversing some path. You are allowed to change this path. You are allowed to change the structure of this path. You are allowed to move the keys on this path. So mainly you can move more, but mainly in splay or whatever heuristic we will be seeing, we only move the elements that appear in the search path. Okay. So yeah, so the other heuristic that I was saying that came before splay tree, it was given by Monroe, and so it is called move to front. So what you do is you search, say I am searching for a element x, and say that I have a root and I have some search path to x. So I do a rotation with the parent, and I finally move x to the root. That is the move to root heuristic. That is, you rotate x and p of x. Okay, so one thing I probably should have mentioned before, the model, binary search tree model, I guess everyone of you know it, but I will still mention the BST model that we are looking at is that I can move, like I have 3 pointers, and I can go to right, left, or parent. So from a node I can move in this 3, or I have these 3 pointers. Yes. So this is the move to root heuristic. And so what is the point of bringing x to the root is that if x has been accessed now, it is likely that x will be accessed in near future. So I'm moving moving x to the root, but this thing does not have, this heuristic does not have a good amortized time. So what I do in splay, why I talked about the move to root thing, is because what we do in splay is a bit similar to this, but instead of doing one rotation, we do a pair of rotation. So in splay, So in splay, the rotation is not this simple. Finally, the accessed element will move to root, which, but not by rotations like this. So in splay, we identify 3 different cases. First is that this is your root, and this is the parent of x, and you have x as a left or right child. So that will be the symmetric case. So then you just do one rotation, you change x, and then px, and this is the terminal case basically. Otherwise, you have a path to x. Just look at the grandparent and parent of x. How it can look. It can either look like this. You are following left left, or you can follow right right, or you can follow left right or right left, right? So the left left and right right will be the symmetric case. So let me first say what I do in this case. So this is x, the element I am searching for. This is parent of x, and say this is grandparent of x. In this case, if I would have done this kind of heuristic, I would have first moved x to p of x, and then move, like the move to root heuristic will do something like this. It will first, okay, let me just think more so that see, these are the subtrees that are hanging at the other sides. Okay, so let me not talk about move to root. Let's see what splay does. What splay does is, it does a pair of rotation. So instead of rotating x with p of x and then then x with g of x again, we first rotate p of x and g of x. So the first step is and then whatever you get from there, you rotate x and p of x. Note that in this step, p of x is actually the g of x of last. So I should write g of x. Did you get the rotation? Let me just draw it here. So what will happen if I do this rotation first? I am rotating this too. P of x comes there, right? Now if you move, rotate again, then x will go to root, then there will be p of x, and then there will be g of x. So at this path like this, so if I remove this x's, you see that the path is like this. So we will call this zig zig. So this case is called zig. This case is called zig zig. So from a path like this, we ended up in a path like this, and x has been moved. So px, if you notice, if I would have done move to root, px would have been here, gx would have been here. But here px remains in the middle, gx comes down from the grandparent to x's place. This is just to mention what is the difference between move to root and splaying, and why splaying might be working. So
Move to root, how can we preserve the ordering property?
the symmetric order property, the BST property. So rotate movement is that property, right? How do you rotate in a BST?
We are rotating here.
Yeah.
I'm not getting the difference between move to root and
This
We're
rotation.
rotating-
Here, see, in a move to root, what you would have done is that you first would have rotated x with p of x. X would have been in this position. Then you have rotated this with this. So the final outcome of move to root of this step, so if you had this, and this is p of x, this is g of x, and this is x, this would have been changed to x g of x p of x.
in left side. Px will be in left side of Gx.
Yeah, pf will be in left side of x, right, true, sorry. Yeah, so when you rotate, the binary BST property is preserved, right? So here also when you rotate means you are preserving the symmetric order property. Yeah. So this is the zigzag case, and the third case is the zigzag case. Zigzag means we have g of x, then p of x, and then x here. This case, here it is similar to this case. I first flip x with px and then px with gx. Then x with gx. So it will look like this only. X goes on the top, then so yes, so this is what we call splaying. So in the terminal case, when x is just the child of the root, left or right, we will do this, and otherwise in a zigzag case we will do this. So let me just remove the middle step, just keep the final step what is coming here. So now this is, so far what I have told you, this is just a heuristic, and we are hoping that this will give us a better amortized time, and we will do the analysis via potential function, and we will see it indeed gives us a better amortized time. And the computation may look a bit magical, so we will see. So yeah, one intuition is why it should work is that if you are doing it on a long path, if you are doing this playing thing on a long path, what it does to the path is that it almost halves the length of the path, or so the depth of each node on that path, that almost gets halved. That is not the case in other heuristic that had been seen before, and so this is why we so far that is the only intuition that we have that it might work. So what is it we are saying that, okay, if I do the self adjustment or the rotations like this, then the path gets almost half. So based on that intuition, or somehow we define this potential function. So you must be knowing that the amortized cost is actual cost plus the change in potential, right? Phi is the potential function, say, in the current state, and after changing it is phi prime. So the difference in potential plus actual time is the amortized time. So if I want to find the amortized time of a sequence of axes, then it will be I equals to given, say, 1 to m, or I want to find the actual time of a sequential axis, then this will be phi. Phi naught is the initial potential, phi m is the potential at the mth after the mth surge. Then this is the actual cost. No, the actual cost. So this is what we are after. We want to measure this actual cost. So if this is some positive value, the amortized cost always gives you a upper bound on the actual cost. So okay, first then we will look for this amortized cost for some axis. So that, as I said, we will do via the potential function. So the potential function will be something like this. Okay. So this is called the sum of log potential. We will see why. So for each node, so think of the balanced binary search tree. What is the cost? We are saying log n. So what is log n? N is the number of nodes that is in the subtree rooted at the root, right? So I have the root and the whole tree is there. So I can say there are n nodes in this tree, and log of that is the cost that we were saying in case of balanced tree, right? So we'll define the potential function something like that. So for each node we will define something called, each node x we will define something called the size of x. Size of x will be the sum of, so here if you in a balanced binary search tree, if you say size of, or any binary search tree, if you say size of a node, you mean the size of the subtree rooted at that node, right? Now here instead of just, so here I should have written should write that size of x is sum over say y belongs to subtree of x 1, right? The number of nodes in the subtree of x. Instead of putting 1, I will put here some weight. So for each y, say let me call it I, weight of I, and then I will define the rank of that node to be log of this size. This looks fair, right? So here we will take discrete 2 log. This is the cost. This is kind of the cost that you get in a balanced tree, that log of the size of the tree, size of the, yeah. So now the potential function of the data structure, okay, I'll just remove this. The potential of the data structure phi is defined as sum of x belongs to the tree R of x. So this is the potential function that we are defining. Now we will look at the amortized cost. Yeah, I said right. I am just assigning some weight to each of the So Wi is greater than or equals to 0, or say not 0, say greater than 0, positive.
And they are assigned different weights or same weight?
Different weights for different items, different elements, but for now say it's fixed in the beginning of the beginning of the analysis. So notice that this potential function, all this thing is in the part of analysis. When you are doing some search, what you are doing is this. You are doing the splaying thing, and now we are trying to prove that splaying is good. Splaying gives you a better, good amortized time. So for that we are defining the potential function, right? So yeah. Is it clear? Do you have any question about what is the potential function or the splaying itself? What is happening in the splaying?
The zigzag is not clear.
In the zigzag case, you first rotate x with p of x, and then you rotate x with g of x.
Then px will be left side of x.
Have I done something wrong?
If I rotate x and px,
Yeah.
then px will be left side of x. Then I rotate x and gx.
Yes.
Then px will be my left side of x. Then you can say size of left.
Is it so? If you rotate this too, x will and then you have x. You rotate this. So then this moves up, and I don't know why you are saying that. Now I move x to p of x. So what will happen? X comes here, px goes here. Okay, maybe you are right. Then right now I do another rotation, x and g of x. X goes on the top, and then g of x. X is smaller than g of x, so g of x goes in the right. Okay, maybe yes. And then is this what happening? 1 second, just let me check. Yeah. Sorry. This is what is happening. Yes. So yes, that's what we are doing. Yeah. Okay. Thanks. Okay. So now we'll claim that. Okay. Yeah. Any other question? Any other doubt? Okay. So we claim that the amortized cost just yeah. So I should write it as a lemma. Let t be the root and x is the axis element. The amortized cost of axis or splaying is at most 3 r of t minus r of x, which is actually order of log s of t by s of x, right? So this is what we claim. So this lemma itself right now may not be looking very surprising, but we will see that this lemma will give us some surprising properties for splay trees, or it will show us that splay trees satisfy some properties. We'll come to that, but yeah. So the statement of the lemma is clear, right? So again, the proof is bit calculative. So we'll just look at case by case and we'll show that the cost is at most this. Cost for splaying is at most this. So in the first step, so if I look at the zig case, what are the nodes whose potential is changing? Only the parent of x and x. So the cost will be at most potential difference. So what was it? Yeah. So here only x and px is changing. So rest of the terms will cancel out. So it will be, say r prime is the new potential. So it will be r prime of x plus r prime of p of x, or say, let me just, instead of writing p of x again, let me just call it y and x. Okay. So the cost will be r prime of x plus r prime of y minus r of x plus, this is the change in potential, and there's be the access cost of 1. Yeah. So then, okay, we just want to, I think here is a 1. Yeah. Okay, yeah. So this we can write as, since r prime of y is greater than r of y is greater than r prime of y, so this we can write as r prime of x minus r of x, right? Y in r prime, y will come down, x will go up. So the potential of the rank of y should decrease, right? So this I can, so then I can, if I remove this 2, I can write that this is less than equals this, right? So this is at most. Similarly in this case also, say I had z, then y, and then x. Again the cost, the potential change of y's, x, y and z will be accounted for. So it will be r prime of x. Are you guys getting bored? Yeah. So can you tell me why it will be this? Why this will be this? So I'm trying to prove that in each of the cases the cost is upper bounded by this quantity, right?
But over there is a t. So over here it should be z of, I mean, r dash x minus rx. That is okay.
R z and R dash x will be same.
Yes, yes.
Yeah, so you were saying that we can cancel out these two terms. Then as we did here, since this term is bigger than this, r of y is bigger than r prime of y, we can write it like 1 plus r prime of z minus r of x minus 2 r of y. R prime of z is less than r prime of x, so I can change it to be r prime of x minus r of x minus 2 r of y. Now I want to upper bound this thing. So what is this? Remember these are all log functions. R of x is a log of s of x. So can you tell me what should be the upper bound for this? Where should I write? If I write that thing like that is can you tell me a upper bound for this function?
Was it last log of this?
Minus s x, yes. No, I want to write it as a plus. What did I do? I cancelled these two terms and then r of x remains as it is. This I replaced by this. This I okay. Let's not replace r prime of z by this. Let's replace r of x by this. So minus r of x minus r of y. Okay. Just some manipulation so that we can get a bound. So replace r prime of x by r prime of y. So we can write that this is less than equals to r prime of x if I replace r prime of y by r prime of x, and then plus r prime of z minus r of x minus r of y. This is what we have. Now to r of x, yeah. R of y is where? Yeah, r of y is more than r of x. So I write it like r prime of x plus r prime of z minus 2 r of x. Is that okay now? Oh, and here it is not 1. We have done 2 rotations, so it's 2 plus. Yeah. So then this will become plus, this will become x. Right. So can you tell, give some upper bound for this function? This is 2.
We want something like log a plus b is greater than log a plus 1.
What is the maximum value of a function log x plus log y?
Whichever is greater twice.
This is a concave function. So can you notice one thing. This s prime of x plus s prime of z is less than equals to, or this is less than equals to 1. No, if I do it the other side. Okay, let me take it to the other side, then it will be, then I'll be able to formulate it as the, okay, so I want some upper bound for this function, right? So instead I look for the lower bound of this function.
Is xy is is xy is tangent.
S prime,
Is xy is tangent.
yes. Okay, so just let me just tell you. This, if you just uh, look at this function, this achieves maximum value of minus 2 when x and y are half. So then from there you will get this term will have a upper bound. So this term, this inequality here will have a upper bound of 2 plus that. Okay, so what do we want to prove? This is 3 r prime of x minus r of x. This is what we want to prove, right? So then that implies I want to prove that 2 r prime of x minus r of x minus r prime of z is greater than equals 2. Right? This is what we want to show. That not this inequality. This inequality what we want to show. So this implies this is greater than or equals to. Now write it as log. Write it as log, right? S prime of x by s of x plus s prime of x by s prime of z. This is what you want to prove. So if you do, if you look for the maximum value of log x plus log y, that's what we get. Or rather, yeah, minimum value of this thing. And we know that s of x plus s prime of z is less than or equals to s prime of x. So if you solve this optimization problem, you get that this is less than or equals to minus 2. That means this term is greater than or equals to 2. So I get that this is less than or equals to minus 2. Anyway, just some calculations. So this is the zigzag case, and then if we look at the zigzag case, that will be also similar to this. So z, y and x, move x to the top. So then here also I am doing 2 rotations, and the cost again it is r prime of z and you can do this. Okay, do you want me to do the calculation? You can just do this manipulation. You can prove that it will be less than or equals 3 r prime x minus r of x. Can you see? Okay, just let me do this then. Yes, we can write this from here, right? R prime of x and r of z are cancelled out. Have r prime of y. Like the way we did it here. This is the same expression, I think. Yes. So you can do this and you will see that this is coming out to be 2 r prime of x minus r of x. Okay. So if you notice that here we got 1 plus r prime of x minus r of x in the zig case. In the zigzag case we got 3 r prime of x minus r of x, and in this case we got 2 r prime of x minus r of x. So zigzag is looks like the costliest operation among these three, just to mention. Okay. All these calculations are there in the paper, so you don't need to copy the calculations. Just
You meant zigzag is the first.
zigzag, yeah, sorry. Zigzag is the costliest one. Okay. Okay, so that proves this lemma. So we didn't get much insight from this proof that why this playing cost is, the amortized cost is this, and what use it is of. Like, okay, I'm getting log of something which looks like this can be n, so it's something of order of log n kind of amortized cost I am getting. That is what I was getting in that case as well, in the balanced tree as well, because I'm doing only one operation for that. I'm getting this much. So what good it is doing. So look at, if you are looking for the amortized, okay, I hope by now you remember the rotations. I'm just removing them, or I can remove this part. Can I remove this part? Yeah, so if I am doing m operations, if I am doing m searches, then what would be the total cost? The cost of one operation is that. What would be the total amortized cost?
You have already given a bound with the value of testing.
Yeah, that is for one operation. I'm doing one search x. I'm saying that I'm doing a search of, so I have a sequence of x1, x2, dot 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 xm.
Right. An upper bound will be able to that.
Yeah, so just sum it up, right? I equals to 1 to m, 1 plus 3 r, what is that? Yeah. R of x. So x is xi, and t is that, say, ti, the current root at that position, at ith search. So if I do, x is in the next step, x is the root, right? So at I plus 1th step, xi is the root, so I will cancel these things out, and what will I get? So xn, yeah. Right?
In plus.
M, yeah.
No, x in plus this.
M plus this thing, yes. Right? So yeah, so this is the total cost that you get. Now the yeah, so are we? It is not clear. Are we still? Is it a good heuristic? We are getting some better amortized time, some good amortized time. Now I will say that it is more than that. So what? Uh, where we start? What was the question that we started with? We said that okay, in a balanced tree, if I am searching, I can do log n, but I want to do better. So, or can we do better than that? So we said that okay, don't look at the individual search cost. Look at the cost of search of a complete sequence, some sequence, and look at the cost that I incur for that sequence. Now we talked about some easy sequence, like we saw that if the sequence is sequential access sequence, that's the 1, 2, 3, 4, dot 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 n, then we in binary search tree we can do linear time, that is order of 1 amortized cost per search. Just a little bit of modification, we just said that okay, we can keep a pointer from where we left the last search, right? Now this is what we are looking for. We are trying to say that can we achieve order of 1 amortized cost. So that is where we will end. So how much time do I have? What is the time right now? So we will look at some properties. So we are saying that okay, we want to do order of one cost, and in that scenario where we don't know the sequence in beforehand. So it can be some cases that you know the sequence beforehand, like you know that this is the sequence you are going to search for. What would be the best thing to do? Any idea? No, I want something like a constant amortized time per search. Or maybe not, maybe I won't be able to do that, but what is the best we can do?
If I know the sequence, then I will make the next node in the sequence the root of my tree.
So if it is the case that the next element that you are searching is always at the last level of your tree, like it may be the case, right? Say you have some tree and it goes on. So this is the tree you have, and you search for this node first. Okay, this is the node you have searched for, and you move this node to the root by some means, somehow. Oh no, sorry, not this. You search something, and then you saw that this is the element that. So this is the element you searched right now, right? Because you have moved it to the root. This is the one you search, and then you saw that okay, this is the next search element. You moved it to the root. When you move it to the root, whichever element, so this path will restructure, and say this is the element that will come at the last level, and you are searching for this element in the next step. So after you search for this element, you will the next element you have to search for. So the next of next is always at the yeah. So do you get what I am saying? See, this is the element A I am searching for in the next step, and this is B. So my sequence is like, and this is say C. So I have searched C, then I have A, and then I have B. So now when I move A to the root, I am bringing these guys down, and this is what something I have to search for. So that may not be a good idea. And if I am not allowed to restructure my tree, then what will you do? Just any idea, you can just think out loud, say anything, whatever comes to your mind. Say I am given a sequence of x1, x2, xn, and I am saying that m is larger than n, right? So some elements are coming again and again. So say if I am not allowed to restructure the tree, yeah, so whichever element is more frequent, it is helpful to keep that is at a lower depth. So the most frequent element, if I keep it at the root, and the next frequent elements are in the next layer, if I do it like that, then it will be this is the best I can do if I am not allowed to restructure my tree, right? So when you know the sequence, this something like this you can do. So this is called static or offline case, when you know the sequence beforehand. The sequence is not coming online. So, but we will see that splay also good. Splay is good in this case, and splay is good when you don't know the sequence. So we will state this as some properties. So you will not need to remember the potential function, but I will like to mention that this, and there is only one other potential function that have been used in this kind of analysis. This is called the sum of log potential, and this potential function lets you prove this bound, and this bound is good. As you will see that in the whatever we'll be proving now, we'll be using this lemma as very crucially. So, but yeah, why this potential function exactly? People are looking for that. So, first is that is play as good as a balanced tree? It is, that is, you can see from this result itself, right? If you put, so yeah, so when we are doing this, looking for this comparing splay with other trees, or which we will be calling balance properties, static optimality. So the key thing is that if you, oh, I just removed it. So this is, just let me write it here. What is r of x? R of x is log of s of x, and s of x is sum of I belongs to tree of x, weight of I, right? So this I said that take any weight, and here in the total proof of this lemma, this weight whatever I would have taken, unless means as long as it is positive, it does not matter. So while proving these properties, we'll use that fact that I can put anything for that weight. Okay, and the thing before going to that property, notice one thing. If I keep the weight fixed throughout my analysis, what is the decrease in potential? What can be the maximum, an upper bound for decrease in potential? So what is the initial potential? So what is the potential of the data structure? This is the potential, right? So what is the initial potential? This is sum over all the nodes that belongs to the tree, log of size of that. So if, and this is sum of wi. So let me, so if I write sum over I wi to be capital W, then I can write it to be log of capital W, right? So this is the initial potential, and the potential is changing. So the next term can be at most, at least this. So say I am saying it's W star I, where W star I is the smallest among Wi. Okay, so this is an upper bound on the decrease in potential, because at this is this minimum the decrease you will have, negative term you can have in this. So yeah, so now we will be looking for the cost, what splay takes compared to balanced tree, compared to this kind of when we know the sequence, this is the best we said. So this is called static optimality. So we'll compare splaying. So we'll always use this as a potential difference. So I removed that part as well. So the actual cost is amortized cost plus this, right? So amortized cost will come from this lemma, and the potential difference will come from this, because we want a upper bound, right? Upper bound of the actual time. Yeah, so now we have 15 minutes and we'll look at 5 properties. Okay. I'll just remove this. So first, as I was saying, when I am comparing it to the balanced tree, it is easy to see if you put all the wi's to be 1 by n, what happens? Capital W is 1, right? So what is the amortized cost? So I am looking for sum over I. So just assume that I am accessing m elements. So Ti, this is the value I am looking for, and I want an upper bound for it. So tell me what it would be. What is the amortized cost? What? Huh?
Initially, the root contains all those elements, so it was log n. And
What is the amortized cost? This is the amortized cost, right? M plus what I had written here. What was it? M plus 3 R of t minus R of xm, right? Right? Less than equals to. So this is the amortized cost. What is that? That is log of S of t by plus the potential difference. What is the potential difference? If I write it, this is sum over x belongs to t log of capital W by W star I. Okay. So what can this value be at most?
log n.
Log n. This can be log n at most. You are summing over all the nodes. So this can be n log n, right? So then, and what is this? So this is n log n, the potential difference, and this is the amortized cost. This is the potential difference, right? What is this term? This term is in size of xm. So if I want an upper bound, this is same, right? This is also in log n, right? So it is m plus order of, or I should write it like m plus n log of Is it clear how it is coming from here to here? What is the weight I said I am putting? 1 by n. Sum of W is 1. So this can be S of t is capital W, this value can be 1, this value is 1 by n, this minimum can be 1 by n, so this will be log n again, right. So I am getting a log n here plus m plus log n, so I can write it like this. Okay. So the next thing that we'll say that it is static optimal. So okay, just let me say one thing. What I said, what is static optimal? That I know the sequence beforehand. The sequence is not online. I'm in an offline situation. So in an offline situation, it would be like minimum over all the algorithms that I can do, and the cost of that algorithm A, right? So this is the static optimality, optimal value that I can have. So if you know the entropy bound thing, or just then believe me, from entropy bound you can get that the static optimality bound is like this, that if every item is accessed once, at least once, then the total access time Fi is the frequency of the ith element, the element that I am searching in the ith step. So this is some bound you can get using entropy bound, and this is the optimal you can get in a static case. So when you're yeah. So we'll see that splay satisfies this property as well. How? So as I told you, the in all the 5 properties you will see, we'll just put some values for the weight, and the analysis will follow. So can you tell me what should be the value I should put in here? See, the potential difference, the decrease in potential will be n log n, right? Plus 1 m you will get for the from this plus 1 term of the amortized cost, and the total thing I want to be this thing. So then what should be the weight? Fi is the frequency of the element accessed at the ith step. So if I put the weight to be Fi by m, right? Then what would be capital W? Sum over Fi is M, right? So this is 1. So again if I write it like this, this term, the numerator of the log will be 1 and the denominator will be Fi by M. So I will get log of M by Fi. Is that clear? Okay, let me just write it. So what is the actual cost?
Every time is access at most to 1, so it will be 1 by m. Yeah.
Hmm.
So it's a minimum number.
Right? So this is right? Am I doing something wrong?
X plus 2.
Oh, sorry. Here also I missed the summation term. That's why you guys were looking so. This is this, right? Yeah. Right? You are looking very confused. No, him. Are you not following the calculation? You can do the calculation yourself. Then you will. It will be like you will see that it's just the cleverness is in what weight you should pick up, so that you get the bound. Yes.
It's about Fi at least 1. So W is 1. So it can be almost that term.
If I is at least 1, yeah. Hmm. Right. So okay. So the next thing which people have seen before is that uh, is called the static finger property. So what happens if in the tree I have a extra pointer at some node which I call a finger, and if I can either start my search from the root or I can start my search from the finger. So finger is something which I can randomly access. So whichever keys are close to the finger, them I can access them quickly. So the static finger thing says that it's a node where you have put the finger and you don't move it. A dynamic finger would be you can move the finger. When you are accessing the finger, you can move it as well. So the static finger property says that if I have a finger at say some position F, so let's say F is a fixed element where I have a finger, and then the total cost is, total access cost is order of n log n plus okay. So it says that log of whatever your distance from the finger is. Ij is the key value of the key, that is element at the jth step. So this gives you the absolute difference between the key value of the finger and the item accessed at the jth step. So if you see that this n log n plus m is something like, n log n is something like the setup cost, m is one cost you are spending per access, and this is the extra term that you are having. In everywhere where we are writing it like this most of the time. So yes, so we'll see that splay also we can give a upper bound for the like this for splay as well, and based on what we are doing so far, what can I pick as the weight? I can keep fixed weight or I can change the weight as well, but okay, here we will keep fixed weight and the weights will be so I should write yeah, if I take this to be the weight, should I take this or this plus the distance of that particular element from the finger plus 1 whole square. You will see why I am taking that plus 1 whole square. So then what is capital W? Can I just give an upper bound for the series? So this is can I write it like this? Plus 1 is because f minus f would be 0, that's why there is that plus 1 that I am taking in the weight. Right? What is the sum of this series? order of 1, right? This will be constant. So I can write it as this. So W is again order of 1. And again, then what would be the total cost? I'll have a potential change of n log n plus m plus by this. I can write it what, some k, or what will I write? Write it I. So I'm just changing the running indices. J minus f plus 1 square, right? And the second address. Sorry, just 1 by this. Minus. Right, so this is ij. Ij means the element I am accessing at the jth step plus 1. Now with log I don't need the whole square, I can put it in the constant term here. So I can write it order of this, right? Okay, good. So splay satisfies the static finger property. The next, what is that? Your class is still, no. Okay. Okay, I'll take 2 more minutes and I will just say another property and I'll then leave you with the main conjecture of this area. So the next property is called the working set property. So okay, so let's not look at it in this monotonous way of proving that okay, splay satisfies this. I am just putting this potential difference, I am just putting the amortized cost, and then I have this, I put some weight and I have this bound. That's okay. But what is actually happening? What are we saying? When I am saying a static finger, I am saying that if I look, if I have a particular place where I can go without spending any cost, then I can do this much. So what is the goal? We, instead of saying a vague bound of m log n, which is if you look at in the worst case, we are trying to give a better upper bound. So in different cases I am saying that okay, in general you cannot give a better upper bound, but if you have this kind of thing, you can give a upper bound like this and splay satisfies this. If you have a balancing property, then you can give an upper bound like that and splay satisfies that as well. If you know the sequence in advance, then you can give an or at least the frequency of the elements in advance, then you can give an upper bound like this and splay satisfies this as well. So the next thing is also in that same theme that okay, if the elements are not accessed, like whichever elements I am accessing, they are accessed, so I am accessing say 5 right now, and in next time I access 5, there has not been many elements that has been accessed in between. So it's like the RAM concept that you have a lot of things in your hard disk, you bring something to the RAM. Whatever is in the RAM you can access fast, right? So if I have accessed something before, that should be in closer to the root, and it should be less, I should be spending less time to access that element. So the working set property says that if you are searching for few elements again and again, it should not take you a long time. So it says that so let for an element j, tj be the number of distinct elements searched after the last access of tj. Access of j. So if it is the case that I have not searched a lot of element after the last access of j, then I should be searching it faster. So as you can see from the splaying thing, that if something has come to root and I haven't searched for a lot of element, that should be staying closer to the root. So and you can prove using this set of tools that if based on this tj I can give a bound that okay, in a sequence this is the maximum time you should be taking. So the bound is like this: order of n log n plus m plus sum over I equals 1 to n log of tj plus 1. Okay. So I am saying, see, this is the cost you have to spend, log n plus m. After that, if tj is small, you are not spending a lot of time. That is what the working set property says. And if you take the weights to be, weights to be 1 by tj square, then you can prove it. But one thing you should notice, that 1 by tj square, tj is a thing that is changing with the sequence. So the first element you accessed will have a cost of the last element you accessed will have 1 by tj square to be 1. The element you accessed before that will have 1 by tj square to be 1 by 2 square. The element you accessed before that will have 1 by 3 square. So the weights will be like 1 by 2 square, 1 by 3 square, I guess that is, yeah, up to 1 by n square. And when you access some element, you will need to update the tj accordingly. So what will happen? If this is where I have accessed j, and now at this time I am accessing j again, say at time t I have accessed j, at time t prime again I am accessing j. Now at this point, say in between this I have accessed a lot of elements, but the number of distinct elements that I have accessed is k, say. So k distinct elements has been accessed here. So at this point of time tj was 1 by k square, but now I access j again. So tj was 1 by k square, now I access j, after that tj becomes 1, right? And all the elements that is in between this, for them, for their next access, one element has been like one more element has been seen before their next access. So if their value was 1 by I, that should be changed to 1 by I plus 1, right? And whatever was before this j, their value should remain the same, right? Because j was after them before as well, now also j is after them, everything after them before their next axis is there. So these values will just permute themselves in here, and this is this 1 by k square, this is the thing, order of if we look at capital W, it will again be order of 1, and you can do the same calculation and you will see that it satisfies this property. We can talk about a unified property where the cost will be minimum of this log, and yeah, this two log, the finger and the working set. So okay, so we are seeing that okay, splay is some heuristic for which we prove that okay, it has some good amortized cost, and based on that so what we are picking out here, we are picking out, so if you look at this, we are picking out some property of the sequence. So if this sequence has such a property, then it is good, or if I have such a structure, then splaying is good. Now the thing is that is there, so I can say it like, what is the amortized cost here? If this term is very small, because this is log of something, so then I am almost reaching the amortized cost to be almost constant, order of 1, but not yet there. So is it the case for any sequence I can do that? Is it the case that splay on any sequence the amortized cost would be constant? So the dynamic optimality conjecture says that when you do not know the sequence beforehand, so that is the main big open thing here so far. Okay, another thing to mention, I told you that there is something called the dynamic finger, and the dynamic finger also has been proved for splay in 2000 by Cole et al. So I'll just mention that. Finger for splay. I guess the spelling is correct. So this was a sequence of 2 papers, very long, total almost 100 pages probably, and they proved that the dynamic finger property also holds for splay. Dynamic finger means your finger is allowed to move. I am not going into detail, I am just telling you that splay is so far splay is still a very good candidate for saying that when I don't know the access sequence, and in that case if I am looking for something like some algorithm which will minimize this cost, some algorithm A, so splay can be splay is a good candidate for that algorithm, and the conjecture that was given in this paper itself is called the dynamic optimality conjecture. And that says that yes, splay can do a order of 1 this thing, but amortized cost per search, but this is still open. We don't know if we can prove that, but there has been many approaches towards this, and we have looked at, so people have looked at many different properties for sequence for which splay, and there is another variant which is called the geometric view of binary search tree. So for them different kinds of bounds have been proved, but this is still open, and there had been two other conjecture given in the same paper. One is the traversal conjecture, that if you are doing a pre-order traversal, so and if you so if your access sequence is a pre-order traversal of some tree, then also it should take constant amortized time, but that conjecture was resolved by Tarzan himself, and there was a conjecture based depending on conjecture on the update time. So I haven't talked about the update of splay tree. So what if I'm like update by that I mean what if I insert or delete? How much time that will take? So searching takes this much of time. So they have proved in this paper that that also takes order of log n time only. Yeah. So yeah. So that's all. There is a lot of work has been done on this towards this, but yeah. So you can look up, take up the open question, look for it if you want to solve, or there are many other interesting properties you can look for, which kind of sequences would be good. Yeah, that's all. Thank you. Yeah. Just let me. Oh, so there are many papers on this particular splaying and the geometric view that I mentioned. So this paper I mentioned, this is the self-adjusting binary search tree by Tarjan. There is another paper which gives us traversal conjecture, resolve the traversal conjecture, that is also by Tarjan. And geometric view paper is by Eric Demain. That is the next. You can say another way to view at binary search trees. And there has been many papers, so you can.
So I'm saying like guide me where you have
All
all the papers.
the papers you want, there was 14 papers we did.
Whichever is like we can start off with. You make that decision.